Good morning, everybody. Just getting everything ready, all that fun stuff. I hope everybody's doing well. You probably maybe have noticed that I've updated a few thw on the My Open Math website. So I want to go ahead and take a few moments to this morning to kind of go through that, to showcase a few of the changes I made, not major changes, but just things that should be there to help you out so that when you go to kind of study for an exam or something like that, it should be helpful. So let me hop over to that. All right, so here's the My Open Math page. Let me go in the student view. All right, nothing here has really changed. We're still finishing out 11.6 today. And then 11.7, just to give you a heads up, there's no lecture on it. So that's why it says 0 days, but there is an assignment for it. So if you scroll down, you'll be able to see under the Unit 3 sequences and series, you'll see an assignment that's due down there. It's due on next Wednesday. And we'll start into 11.8 today. But the things that I did. All right, so let's go into the Unit 3 material down here. Which has all of the sections. You'll see if you expand section 11.1, I actually finally edited and uploaded the videos yesterday. So you could see the lectures for 11.1, part 1 and part 2. Also, I embedded here a lot of the prerequisite information that we run into as I'm going through examples. So if you open up, for example, the lecture notes there, they're slightly changed, not a big deal. The examples are the same. They're not slightly changed, not in this one because I haven't uploaded the new version of it. But my new lecture notes have like for this example, you'll need to probably review indeterminate forms and L'Hopital's rule. So there's a video for that. So anyhow, since we've already gone through it, you probably don't need that stuff. But if you do have a problem with L'Hopital's rules or L'Hopital's rule, there are videos right here, prereq videos right here for that. If you don't remember factorials, there's a video for that, though it's very fast to remember that. Same thing, squeeze theorem or limit laws, all that stuff is there. So that's how I've kind of redone things. So each section has now I wonder if I uploaded. Yeah, okay. So here's what the new lecture notes look like. So for example, 11.2, prerequisite information before even getting into the material is just to recall all what geometric sequences and series are. And then, you have the lecture notes themselves. And then sometimes within some of these lecture notes, there might be, I don't think there is here. Oh yeah. There might be like a prerequisite piece of information that you might need. So again, there'd be a link to that. If you're like, I don't remember this from my pre-calculus class, well, there you can actually review that stuff if you want to. So anyhow, so that's just me kind of cleaning up. It doesn't really affect anything other than allow you access to the lecture videos now. I've only done it for chapter 11 just because it takes about 8 hours to do all that. It took about 8 hours, I should say, to do all that. So just a heads up, I only got through the section or chapter 11 material as far as what we've gone through so far. All right, so let me go ahead and go to my laptop and share my screen there. And let's start, or continue, I should say, in through section 11.6. 11.6 was, or is, the ratio and root tests and absolute convergence. And these, as I've mentioned, are kind of the coolest tests around. Oh, I should also mention something important. I'm picking up my wife from the airport. So I will not be in office hours today. So I have to cancel office hours because I'll be picking up my wife. So I have to leave right after class to do that. So anyhow, we were talking about absolute convergence and then the ratio and root tests. And I have an extra example I included here. So I'll fast forward a little bit. We what else we do? We said that absolute convergence implies convergence. So if you're asked if a series converges, and there are some negative terms in that series, it's a good idea to go ahead and just take the sum of the absolute values of those terms. In fact, I want to write that down. It's so important. So let me go ahead and write that over here. When given a series, summation a sub n, okay, and asked for convergence or divergence, because we really want absolute convergence, if we can get it, then it's kind of useful to just see if the absolute value of the terms, when you add those up, if that series converges. So I'll say first check summation of the absolute values of the terms. And that's because if that converges, then the original series has to converge as well. But you've actually, in that process, proved two things. One, not only does the original series converge, but it converges absolutely. And that's a tighter form of convergence. So that's kind of neat to be able to do that. If, on the other hand, that summation of the absolute values diverges, well, then you kind of have to remove the absolute values and recheck the original series to see if that does converge. So you still need to check the summation of a sub n to see if it converges conditionally. Okay. That is, in my opinion, the best way to do it. It can at times lead to a little more work, and it can most of the time lead to a lot less work. So it is kind of a give and take. There are moments where it does, because somebody hands you a series and you decide, okay, well, let me just see if the absolute value of the terms when I add them up, if that converges. If it does, you're done. Yay. You haven't spent any extra time. If this doesn't converge, then you've spent a little extra time than you should have, and you have to then check to see if the original series converges without the absolute values. So, but some students will ask, like, well, if you're asking me if a series converges, why don't I just check to see if that series converges rather than its absolute value? Because generally a second question is, what about the absolute value of the terms? Will that converge? And so it's just much safer to start with the absolute value, because if the absolute value, the sum of the absolute values converge, then this series will converge as well. You kill two birds with one stone. So that's just a heads up. Let's see, what else did we do? Then we started talking about rearrangements. And this was something that I updated in my lecture notes yesterday. So I found a cool little visual of this, and I loved it so much that I want to showcase it for you guys. I just forgot to load it up prior to lecture here. So let me go ahead and quickly download that to my desktop, and then I will showcase this. Give me a moment. Download the desktop. I don't need to download the player. Give it a moment. For some reason, it's not downloading. Shoot, it's just not. Oh, here it is. Okay, save as. You guys can't see what I'm talking about, but I'll show you in a moment. 11.06. I will showcase this to you. Let me share my desktop. Which one is it? This one. Okay. So as I mentioned before, if you have a series that is absolutely convergent, in other words, the sum of its absolute values converges, then we would say the series converges absolutely. And no matter how you rearrange the summation, it will converge to the same number. That should make sense to us, right? You add up 1,000 terms, no matter which order you add them in, it should add to the same value. However, if you have a series that's conditionally convergent, and that's what the alternating harmonic series is. If you were to add up if you look at the summation of the alternating harmonic series, which is 1, -1/2, plus 1/3, -1/4, plus 1/5, and so on and so forth, that actually converges by the alternating series test, but its absolute value does not. The absolute value of its sum, 1 plus 1/2 plus 1/3 plus 1/4, that's the harmonic series that diverges. So the alternating harmonic series does not converge absolutely, but it does converge. Therefore, we would say it's conditionally convergent. And what I had mentioned on Monday, our last lecture, was that if you have the interesting thing about conditionally convergent series is that you could reorder the series in any order you want to get a specific value. So in other words, if I want, so target for the series sum, let's say I want the series to add to a half. Okay. Then let's see, show rearranged series. Yeah. So to get the series to sum to a half, it would be 1 minus 1/2 minus 1/4 plus 1/3 minus 1/6 plus 1/5 minus 1/8, and so on and so forth. That's the ordering that I would do to make that alternating harmonic series add to a half. If I want to add it to a quarter, let's get it down to a quarter. There we go. It would be this summation, which is different than to add it to a half. So this is just kind of an interesting little applet that shows that, or at least demonstrates, it's not a proof, but it demonstrates that you can rearrange the order in which you add the series to get it to any value you want. If I want to add it up to become a negative 0.78, this is the order I would use. Very, very interesting. I just think this is just fascinating. So anyhow, that's the weakness with conditionally convergent series, is that you and I could have two the same conditionally convergent series, but the way that I add up the terms and the way that you add up the terms might be different. So we get different summations for that. And that is obviously very frustrating. So just a heads up. Anyhow, let me go back to my laptop here. I think it's just such a neat idea. All right. And so we did that yesterday. And let's see, or Monday. And then we went into the ratio test. And the ratio and root tests have the same condition, which is that you take this limit as n goes to infinity. And the ratio test takes the ratio of the next term in line to the current term. If the next term in line is greater than the current term in absolute value, that means that limit will be greater than 1, which means the series is growing, and so our series will diverge. However, if the next term in line, a sub n plus 1, is less than a sub n in absolute value, the series is decreasing. It's getting smaller and smaller. And that means that ratio is less than 1, which implies the series converges absolutely because we're taking the absolute value of the terms. And finally, very important, if you use the ratio test and you get that this limit of this ratio is 1, then the ratio test is inconclusive and you have to do another test. And then we did some examples. And here's where I'm going to reference my my modified lecture notes to make sure that I didn't include an extra example for today. I think I did, but I just have to find it. Fast forward. N squared. Okay, we got that one. -1. Yep, got that one. And then the root test. Aha. Okay, so I'm going to sneak in one extra example here of the ratio test. And I'm just going to sneak it in on this page right here. All right, so let's just do one more example, sneak one in here because we can, okay? So let's go ahead and pretend, and I'll do this in a different ink so that it's completely different. Determine the convergence or divergence of the following series. N equals 2 to infinity of -1 to the nth power over the natural log of n. So in this case, you can see it's an alternating series. And if you didn't test the absolute value of it first, you could do the alternating series test to showcase that as written, this series totally does converge by the alternating series test. And we will end up having to do that. But really the question is absolutely convergent. Whoops. Conditionally convergent or divergent. There's the series. Does it converge absolutely? Does it converge conditionally? Or is it just divergent? I can tell you right now, it's not divergent. The reason why is it's an alternating series. It's decreasing and the limit of 1 over natural log of n is tending to 0. So I happen to know that the series as written totally does converge. Okay. But let's go ahead and test for absolute convergence. So absolute convergence. I'm going to do the ratio test. Remember, up to this point, to test any series that have negative terms, we really only have 3 tests. The first one being if it's geometric, which this is not, then you can use geometric series. Otherwise, if it's alternating terms, which this is, you could use the alternating series test. Or in any case, you can use the ratio test to test for absolute convergence. Okay. So ratio test here, we're going to take the limit as n tends to infinity of the absolute value of the n plus first term. Now, here's the deal. I mentioned it last time, but if I test the n plus first term, there's really no need to write that -1 in there, right? Because you're taking the absolute value. The other thing I want to mention to remind you of is it's the ratio of a sub n plus 1 to a sub n, but that's the same thing as saying I'm taking the a sub n plus first term and multiplying it by the reciprocal of the nth term. And the reciprocal of the nth term is just the reciprocal of that right there. So it'd be natural log of n over -1 to the nth. And this, I just want to do this because this is kind of a nice case, basically. It showcases a specific thing we need to do here. So I'm going to remove the negatives from there. This limit as n goes to infinity. And I technically don't even need the absolute values anymore because as n goes to infinity, the natural logs are going to be positive. So I don't have to worry about the absolute values. Now notice this is going to be infinity over infinity. That's why I kind of wanted to do this example. So this is going to be a L'Hopital's ready style of problem. I think at this point, we're all okay with just using L'Hopital's, even though technically speaking, we're doing this with discrete variables. N is supposed to be natural numbers. But let's just pretend as though it's a continuous variable x for now. Okay. So using L'Hopital's rule, we get the limit as n goes to infinity. The derivative of natural log is 1 over n. Derivative of the other natural log is 1 over n plus 1. And then you modify this, right? Limit as n goes to infinity, a little bit of algebra. This is going to be n plus 1 over n. And we know that's going to limit to be 1. And so therefore, this test is inconclusive. There you go. So I just can't remember if I had a test that arrived the inconclusive result. So I wanted to showcase that in an extra example here. So the ratio test, when you get that limit to be 1, ends up being inconclusive and you have to try something else. Well, since it's inconclusive, I can tell you right now, at least, that the there's no way. Actually, I suppose I could do. Yeah, I suppose that I could do the absolute value. Let's see. So do another test. You could try the absolute value. For right now, I'm just going to go ahead and just make the mention that this right here, the original series, is alternating. Since the ratio test kind of bottomed out there, I'm just going to go back to, well, let's look at the alternating version of this. B sub n here is 1 over the natural log of n. In other words, if you take a look at this without just the non-alternating term there, we know that the limit of that non-alternating term as n goes to infinity is 0. And we also know that if f of x equaled 1 over the natural log of x, that would imply that f prime of x would equal times 1 over x over natural log of x squared. So that'd be a negative 1 over x natural log squared of x, which is less than 0 for x greater than 0. So we know that the sequence, the non-alternating sequence here, tends to 0 and is decreasing. So that implies convergent by alternating series test. So we know the original series is convergent. Now the question is it absolutely convergent? In other words, if I were to force that numerator to be just a positive 1, can we force it to be convergent? And this is going to be very difficult to show, actually. I don't know if we can, because if you try to compare it, I'm going to say it diverges, by the way. If you try to compare it to maybe this, it is true that the natural log of n is less than n. If you think about the graphs of 1 over or natural log of x versus x, you can easily see the y equals x is greater than y equals natural log of x. So it is true. And then that implies 1 over the natural log of n is greater than 1 over n, which is greater than 0. And we happen to know the summation 1 over n is the divergent harmonic series. Harmonic series. So we have divergence below implies divergence above for their series. So I'll say hence or implies the summation 1 over natural log of n diverges, and that's by series comparison test. So in the end, the original question was, does that alternating series converge absolutely, conditionally, or does it diverge? Well, we know it doesn't diverge because we know it converges as written by the alternating series test, but we've just found out the absolute value of the terms when you add them up forever and ever, they don't converge. So this series is conditionally convergent. So when you have a conditionally convergent series, you have a lot of extra work on your hands. Yeah, so it's being asked, why did I have to move over to the series comparison test? Well, it's because when we did the ratio test to determine if it's absolutely convergent, it ended up being that the ratio test was inconclusive. And because it was inconclusive, I had to decide, well, okay, I want to see if it converges absolutely. Let me take a look at the absolute values of its terms. So let me take a look at the summation of 1 over the natural log of n. That's the absolute value of the terms. And so then because the ratio test was out, I had to basically try something else other than the ratio test. We have a lot of tests. We have an integral test. We could do geometric series. However, this is not geometric series, so we couldn't do it here. We could do a divergence test, but that won't work here. We could do a limit comparison or a series comparison test. And I just decided to do a series comparison because I happen to know n is greater than the natural log of n. Therefore, 1 over the natural log of n is greater than 1 over n, and the series of 1 over n diverges. Thus, the series of 1 over natural log of n must also diverge. So the question is, we can do any other test that works after the main one to show the conditional part. Yeah. It's basically that if the ratio test or the root test end up being inconclusive, you have to switch gears. You can do any other test you want to see if it converges or diverges, if the absolute value of the terms converge or diverge when you sum them up. But for the original series, so let's just say that I started here, because remember, after I got to the inconclusive part, I just said do another test, right? And then I immediately did the alternating series test. But let's pretend that I didn't. Let's say I immediately just went to the series comparison test to see if it converges absolutely. Because again, if it converges absolutely, there's no need for me to talk about the alternating version of it. The alternating version will converge if the original series converges absolutely. So let's just say I decide, let me go ahead and focus on the absolute value of those terms and add them up forever. And you do a series comparison test and find out that if you sum up the absolute value of those terms, it ends up diverging. Shoot. Well, I still have to answer the question. Does the original, so I know that series doesn't absolutely converge. Okay. But I still have to then consider, does the alternating series converge? So I'd still have to go back and do this one no matter what. So I kind of knew that was going to happen. So I just decided to do the alternating series test kind of early on. That's all. All right. So that was the extra example. I just wanted to show a conditional convergence. You'll see those more and more as we move forward. You don't see it a lot, if at all, in this section, but you see it more and more as we move forward. So I just want to get that in our brains. All right. And then we started into the root test, and I talked about that a little bit, and then we did an example. We still have an example left, so let's do one last example here. The root test is the same as the ratio test as far as conditions go. Like, there's technically zero condition to use the root test, but remember, when you're using the root test, you're taking the limit as n goes to infinity of the nth root of the absolute value of the sequence terms within your series. And that's why the root test will showcase absolute convergence, because you're taking the absolute value of those terms in your series. The only time you're really going to use the root test is when your series is something to the nth power, or some modification of that. It could be to the 2nth power or something like that. As long as there's an nth power that applies to everything, usually the root test is a really good go-to. There are some very special situations where you might have an n squared power. The root test technically is still very good with that too. So the results are the same as with the ratio test. If that limit ends up being greater than 1, you have divergence. I should zoom out to have all the words on there. If that limit ends up being less than 1, you have absolute convergence. And if the limit is equal 1, it's inconclusive. Remember, these tests, the ratio and the root tests, are different from the limit comparison test in that the limit comparison test, where you're taking the limit of a sub n over b sub n as n goes to infinity. The limit comparison test requires that this value, whatever that limit is, ends up being a constant that is positive. That is a requirement for the limit comparison test, a positive constant. But for the ratio and root tests, that limit, even though you're taking the limit of an absolute value, the limit could become 0. That's totally fine. We're okay with that. All right. So with the ratio and root test, it's okay for L being 0. L could be 0. That's fine. Also, totally okay that L could be infinite. That's fine. Okay. So I just want to draw that fine line between the limit comparison test and the ratio and root tests. The ratio and root tests, you're just taking this limit as n goes to infinity of whatever it is at the time. And you are allowed for that limit to be 0 or infinite. If it's infinite, you have divergence. If it's greater than 1, you have divergence. If it's less than 1, you have convergence, absolute convergence. Even if it becomes 0, you have absolute convergence. But if it becomes 1, it's inconclusive. So let's go ahead and do one final test here for one final example, that is. Determine if the following series is absolutely convergent, conditionally convergent. That's what that was supposed to say. It's fixed in my lecture notes. I just haven't fixed my ones I'm writing on right now. Or if it's divergent. Now, taking a look, it's my father who doesn't realize when I teach. So let's see. When you actually let him know. All right. Okay. When you see something like this, right here, you see the nth power. That should immediately tell you it's either going to be a geometric series or root test. This is way too crazy for a geometric series. Geometric series, first of all, geometric series are only going to be stuff like this, a constant to the nth power. That's what a geometric series is going to be. And I can guarantee this argument right in here, that is not a constant. That involves n. N is going off to infinity. So I immediately know geometric series is out of the question. Let's go ahead and do the root test. That's the only, there's no real condition to using the root test. It's just recognizing it's the nth power. So let's do the root test here. Let's take the limit as n tends to infinity of the nth root of the absolute value of a sub n. Okay. So here we go. That's the limit as n tends to infinity of the nth root. I'm kind of making this bigger because we have this mess going on here. Absolute value of our sequence term right there. So let me plug that in. Say 5n minus 3n cubed over 7n cubed plus 2, and that is being raised to the nth power. Something that you need to realize here is that, first of all, when I take a number, whether that number is positive or negative, when I take a number and raise it to the nth power and then take its absolute value, I'll write it over here. Take a number, raise it to the nth power, and take its absolute value. It's the same thing as taking the absolute value of that number and raising that to the nth power. So basically, you can move the nth power outside of the absolute value. So let's go ahead and start there. This is the limit as n tends to infinity of the nth root of the nth power of the absolute value. That's going to be very helpful, so please remember that. Next thing is that the nth root and nth powers will cancel each other. Normally, if I had the nth root of some number to the nth power, it would be the absolute value of that number. But look, we already have absolute values on that, so you don't have to really super worry about that. That's going to be the limit as n tends to infinity of the absolute value. I'm just canceling these right here. It's going to be the absolute value of 5n minus 3n cubed over 7n cubed plus 2. And the absolute values become kind of important here because you need to know if that numerator is positive or negative and if that denominator is positive or negative. That numerator, I'm going to go ahead and highlight it here. As n goes to infinity, that numerator is negative because it's the cube is more powerful than the first power of n. And so that numerator, oops, I don't want that thin ink. I'm going to use this ink right here. That numerator is negative. And this requires us to recall the definition of an absolute value. If you're one of my former students from a previous course, then you know how my definition goes. The absolute value of something splits into two cases. If that something was already not negative, you could just remove the absolute values. If, on the other hand, that something was negative, well, you're going to force it to be positive by taking the opposite of it. So that highlighted piece there is negative as n goes to infinity. And I'm taking its absolute value. I can remove the absolute value, but I have to force that numerator to be positive by taking its opposite. It's kind of an algebra review, but it's kind of nice to see. So I'm going to go ahead and rip off the absolute value, but I'm going to force it to be that numerator to be positive by taking the opposite of that numerator. The denominator is positive, so I don't have to worry about that. Distributing the negative through the numerator, you get 3n cubed minus 5n over 7n cubed plus 2, and we know that's going to be 3/7, which is less than 1, and therefore that series, waiting for it, that series right there at the very top converges absolutely because that limit is less than 1. The same conditions for the root ratio test. That's for the root. So this is absolutely convergent by root test. Yay. There we go. Good stuff. So in there's a lot of areas where people might have questions. So I'll pause for a moment. You can ask a question or get clarification if you need. So it's being asked, how did I know that it was going to be negative? As n goes to infinity, there's a couple ways you could do it, but the main way that I do this is the fact that n cubed is much more powerful than n. Oh, here's an easier way. If you want to do it algebraically, let me grab this right here. I'll move this out. You could say that's like n times 5 minus 3n squared. I hope you would believe that those two expressions are the same, right? As n goes to positive infinity, that goes to positive infinity. As n goes to positive infinity, this goes to 5 minus 3 times a positive infinity, or in other words, a negative infinity. Positive times negative is negative. So that's an algebraic way of doing it. And Avi is asking, could we also do the same absolute value thing where we force it to be the opposite for the denominator as well? You could, but there's no need. That denominator is going to be positive. So there's no need to do the opposite thing. on that denominator. It's going to be positive. So if you're taking the absolute value of a positive number, you can just remove the absolute value. Yeah. But if that denominator was going to be negative, then you would have to do the opposite case. Yeah. All right. So this finishes out ratio and root tests, and actually all the tests. We are now completely done with all of the tests. Just to let you know, the lecture notes online are done correctly, but these are the old ones still. So giving you a heads up. Let me see something here. I wonder. Give me a moment. I thought I stopped this, but I guess I didn't. I just noticed that my server is backing up, which is hogging my upload speeds. So it probably was causing, yeah, I make all my notes. All these notes are made by me. So I just paused my server from backing up. So sorry about that. So the notes online are better than this last page of notes. But these are all, if you look at the notes online, it has all the tests, when to use them, and that type of thing. And also, the other set of notes that I made here, let me go ahead and share my desktop screen. Give me a moment. Share screen, yes. Desktop, there we are, share. Okay, so here's our My Open Math site. If you go down into the Unit 3 material, down to section 11.7, you'll see the lecture notes there, even though I'm not lecturing on 11.7. So why are there lecture notes? It's because they're not lecture notes. It's actually, zooming in, all the tests that we've learned, when to use them, and some notes on them. So this is my guide for methods for testing convergence or divergence of a series. So there you go. Now you have a nice complete sheet of when to do, what to do, and when. Hopefully that will be helpful to you. So we are done with all of the tests. And so you could see why chapter 11 tends to be kind of a pain for a lot of people. It is actually a very difficult section or chapter, but we're only part way through it. So we still got some work to go. So let's go ahead and now jump into